Thank you for the introduction. So yeah, today I'm going to talk about approximate lattices and algebraic groups. I'm sorry if I spent at first, I hope, quite a long time just explaining what these are, approximate lattices. So some of you might have heard me at the short talks before, but I'll re-explain everything, what we're interested in, what are the questions surrounding these objects, and what we are able to prove, okay, particularly in the context of algebraic. Okay, so let's just get into it, and yeah, let's just talk about the obvious thing, approximate lattices. So we need a few definitions, but I first orient the way you're going to, well, I want you to think about these objects, and essentially the things we're interested in two subsets of G, a group, okay, and the subsets we're going to be interested in how they behave with respect to these kind of operations. So, for instance, the Minkowski multiplication of two sets, which is simply just the set of products. Okay, so fairly simple operation between two subsets of a group. That's really interesting. Okay, so I'm just going to get a few annotations as I might use them. So x to the n plus 1 is simply defined recursively, x to the n times x, with x to the 1 being x, and x minus 1 is just a set of inverses of elements in x. So fairly standard notations, but good to recall them. So the typical behavior of subsets we're going to look into are is what we call approximate subgroups. So we want subsets of the following kind. So approximate subgroups, and it was first defined by Taro. And so we say that lambda in G, a subset lambda in G, of a group G is an approximate subgroup if two things occur. Okay, so the first thing is you want some sort of symmetry. It's not only a convenience assumption, it's really sometimes quite essential. So you want basic symmetry. And the second thing is this, that you have a finite subset of G. So it is finite such that lambda squared is contained in lambda times f. Okay. So why are these sets particularly interesting? So a way we're going to look at them today is the fact that they might be aperiodic, so they might not have any period or any, well, be stable under the action of any subgroup, but they have some sort of global structure with respect to multiplication. So you have they're kind of in between these two behavior of being aperiodic and having a multiplicative structure, and that makes them really interesting. So more precisely, we're going to look at the following thing. So the definition of approximate lattices, and this definition comes from, well, essentially two people. You have the definition I'm going to present is the one to Reshevsky, and some things, let's say, similar was defined before by Bjorklund and Hartwig. Okay, so what is an approximate lattice? It's a subset of a group G, but we want it to have a topology. So it's a locally compact group. Okay, and lambda is an approximate lattice if three things happen. So the first one, given that I just defined approximate subgroups, is quite obvious. lambda is an approximate subgroup. Okay. The second one, well, the second and the third one are going to be related to the second part of the name of this definition, that essentially you want to generalize lattices. So what you're going to do is you want them to be discrete subsets of your locally compact group. So lambda is discrete. But when I say discrete, what I really mean is discrete and closed. Okay. Or in other words, if you take any compact subset of G, the intersection of lambda with this compact subset is finite. You don't want any odd behavior around any meeting point. Okay, and the third one is you want to be fairly widespread, fairly big. You want it to be very large in G, and that is lambda has finite cohomology. Okay, so what does that mean? Well, I will be able to find F, F in G again, that it has finite R measure and such that lambda F is equal to G. Okay. So it's a really big, well, essentially what I'm looking for are really big discrete subsets of a locally compact group. Okay, and I'm going to give you a few examples that are going to guide us through this process. So the examples are the following. So the first example that you might be thinking of is, well, plane lattices. It's boring, but that will do. Okay, so we can be thinking of Zn into Rn, or you can be thinking of SLN Z into SLN R. So when you look at it, a normal lattice is just you replace this condition by lambda is a subgroup. The second example, you have some sort of historical importance, but we are not going to talk about them too much today. The Penrose stylings. More precisely, Penrose styling P3. Okay, so it's not. So what I mean is the set of vertices of this styling, and it's not obvious that it's an approximate lattice, but it's old, important work of De Bruijn that proved that. Okay. The third one, which is a bit more about straight, and what we really are going to be talking about this is what I call piezo numbers. And I'm not going to define them generally, I'm just going to give you an example. So look at this field, say in R and with the usual embedding, and you can define the set of piezo numbers of this field. In the following way. A plus b square root of 2 there, such that a minus b square root of 2 is smaller than 1, where here, like implicitly what I've written here, I assume that a is in z, b is in z. Okay, so it's an algebraic integer such that its Galois conjugates have norm smaller than 1. And this is an approximate lattice in I. If you look at that in R, it's a subset of this. It's an approximate lattice there. That's for the additive structure on R. So that's very nice. You can kind of make this example slightly more complicated by throwing in a few algebraic groups, and essentially you can look at that. What I'll denote SLN. I won't use that notation too often, so it's a bit long, but okay. What do I mean by SLN of the piezo numbers? It's simply these elements of SLN whose coefficients are in the piezo numbers. So what do I mean really? that they land in En plus okay, and there should be one more. Okay, so if I take any element in there, I remove the identity, I have only piso numbers as coefficients. So it's a fairly easy way to define a subset of SLNR, and it's very interesting that it's actually just an approximate lattice of SLNR. Okay, those 2, 3, and 3 prime are going to be what I'd consider as more arithmetic approximate lattices. Okay, the fourth example, which is a bit more than a simple example, is what we call the model sets. Okay, so the model sets, to build these model sets, so are going to be a family of approximate lattices, you need to start with gamma in j times h, where j times h is a product of locally compact groups. Where gamma is a lattice in j times h, in g times h, and it projects well, injectively to h, to g, and densely to h. Okay. So since it sits in there, I have my 2 natural projections, and one is injective on G, the other one is dense. Okay. So these kind of situations are fairly general. You can find such lattices very often, but they're really nice because they allow you to build a lot of approximate lattices in a very efficient way. And to do that, take what we call a window in H. By that I mean just a symmetric, relatively compact neighborhood of the identity in H, okay, and define this set. M is just the projection to G. So I denote it that way, the projection to G of gamma intersected with G prime before you 0. Okay. So M is an example, is an approximate lattice in G. It's called a model set. And it's a particularly regular kind of approximate lattices. And just to give you maybe a little intuition of what's happening here is you can see gamma as a discrete subset of G times H. What you first do is you look around the factor G, you cut a strip of your points of gamma, and then you project them onto G. Okay, so you have this method is called a cut and project. You first cut a strip, then project it to G. Okay.
Can you get Penrose styling this way?
Yeah, that's so the brain's work goes that way. So he shows that Penrose stylings can be built as model sets, and then uses that to say that it's then you can use that to say that it's an approximate lattice. Okay, so yeah, that's the thing. Model sets, actually, all of the examples here are model sets, and there's a very nice theorem by Meyer that has been central in the theory of aperiodic order that says the following. If lambda is an approximate lattice Rn, there is a model set M in Rn such that lambda is in fact contained in a model set. Okay. So you can't actually say that lambda is necessarily a model set because some small things could happen, but you have to be contained in the model set. Another way of saying it, that something else we know now, is you could simply say that lambda to the 4 is a model set. So that's not really part of Meyer's theorem because it was not done at the time, but with new, more additive combinatorial techniques, we can show that lambda to the 4 is already a model set, which is quite nice. Okay, and so this in fact tells you lambda being contained in M and lambda being fairly large because it has finite covolume says a bit more than just being contained. These two have to be commensurable to some sense. Oh, I'm not going to talk too much about that. Okay, so Meyer kind of tells you it's not really a surprise that that all these examples are model sets. And so there are a few questions that arise from this observation. They arise quite naturally. And let me list them. So the first question, really, when you see Meyer's theorem, when you see all of this, and when you see that the definition of approximate lattices is more general than just Rn, than just subset of Rn, is the following. So it's if you have just G, a general locally compact group, you want to ask, are all approximate lattices in G contained in model sets? Okay, so that's just, okay, if you want to reformulate it, does Meyer's theorem hold in greater generality? So there are different ways of looking at this question. You could say, okay, does it hold for all G's, all the time, everywhere? Unfortunately, no, but you can ask for which G's does this hold, or for which G's is this, can we answer affirmatively this question? Okay, so this was first asked by Björklund and Hartnett. Okay, a second question that arises naturally when you have the examples 3 and 3 prime in mind is that, okay, if I have something with a bit more structure than just G locally compact, say if G is equal to, let's say, G of R, so the R points of something like that, so of an algebraic linear group defined over R, for instance, it could be any local field. Okay, so I fixed that. If lambda in G is an approximate lattice, is it arithmetically defined? Okay, so I'm not going to explain because it would take a long time what this means exactly, but is it defined like that? With you have your algebraic group and you just say, okay, it's defined by simply some conditions on the coefficients or something like that, something of this nature. And the third question is, unfortunately, we know that these two don't hold all of the time. So can you at least describe the structure of approximate lattices? What do I mean by describe it? Maybe parameterize the structure in terms of natural families of objects, or and so on. And so, if I want to just answer it very vaguely, okay, in algebraic groups, over characteristic zero fields, characteristic local fields, you can answer very precisely the three questions. So, all, yeah, 1, 2, 3 can be answered. Okay, which is extremely satisfying. The only issue is that it will depend on some. So you will have to look at your group and you can answer depending on certain characteristic of your group, such as the rank or these kind of things. And so so we're going to have a look at a special case where I'll be able to explain exactly what happens. Okay. So can everyone see here, or is it a bit? Yeah. Okay. So I'll describe what we'll try to think about today is the following case. I'm going to have lambda in the group of affine transformations of Rn that are volume preserving. It's a nice group, fairly natural. It has, so I'm going to look at it for n greater than 2 because n equal 1 is not extremely interesting, but it's Meyer theorem. Okay, so lambda approximate lattice. So what can I say there? So the first case is the higher rank case, and usually the more regular. If n is equal to 3 or greater or equal to 3, then essentially everything is true. You're in a wonderful case, and what you can say is that lambda is arithmetically defined. So it's not very precise, but at least in a more precise thing I can say for this talk is that it is contained in a modeled set. Yeah. Okay, so this corresponds to what people usually call the higher rank case, and it's very nice. The other thing is what happens when n is equal to 2. So SLN becomes SL2, which is often a bit more surprising in its behavior. And there you have to really say a few things. So I will not be able to explain everything right now, but I'd say at least something just to show kind of the complexity. Okay, so if the projection of the group generated by lambda to SL2R, so you have an actual projection here on SL2R to SL2R is not contained in a lattice, then the same is true. So then lambda is arithmetically defined and it's contained in a modeled set.
So when you project and lattice, your lattice was maybe non-arithmetic in the technical definition. I don't know what you mean by arithmetic yet. The usual definition in a group like SL2.
Yeah. So yeah, if you project to SLNR, it's going to be arithmetic. If it's arithmetically defined, it implies that
I'm worried about case n equals 2. It projects to a lattice. Many lattices are not arithmetic.
Yeah. So what I'm exactly. So I'm trying to avoid this case, and that's why I asked that the group generated by lambda projects to something that is not contained in the lattice.
That avoids.
That avoids the case.
Where it projects to a non-arithmetic.
Exactly. It can be, so if you want to look at it, it's a similar assumption as saying that it has dense commensurator.
Yeah.
And so that's why it avoids the non-arithmetic case. Okay, so lambda is contained in the model set. In the counterpart of that is that if lambda projects well, you can build one lambda whose projection is contained in the lattice in an SL2R, and that is not a model set and not arithmetically defined in any reasonable sense. So this is kind of a complete description of what happens in that situation. And what I'm going to try to do today is at least give you a few ideas of how this can be proved, or at least how this can be approached. Okay. Okay, so to do that.
What happens with, just before you get into things like nilpotent groups?
So for nilpotent groups, the story is actually, is for every unipotent or nilpotent group, the story is quite nice. It's always to some extent arithmetic. So you don't, it's always
an analog of Pizarro numbers.
So when you just look at a nilpotent group, you don't really have an analog because you don't have enough rigidity. So not exactly, but you have that it is a model set. So
the Meyer's theorem applies.
Meyer's theorem applies. The arithmetically defined depends how strong you want your arithmetic condition to be, but it does not give you that it's just a unipotent group of Piso numbers essentially.
It tells you the Lie algebraic, definable algebraic numbers.
Yes, so you still have some weaker arithmetic conditions, but they're not as strong as just saying that it's something like SLN of some Piso numbers, unfortunately. But it's already quite interesting. Yeah.
You also get that the model set is small in the sense that it's covered by a small number of translates with lambda.
Yeah. So you can. Well, it depends.
You get it there, for instance.
Yeah. So. Yeah, it depends a bit on the situation. It's in general, no. I mean, there should be some absolute number, I think, but it's not clear what it is. And in some situation, you can.
Instead of 4, you can depending on.
Not always. I mean, you can prove it in certain situations, and essentially what you do is you go back to this and use the fact that you know that in that situation to kind of to prove it for slightly more complicated groups, but we don't have any other means than that to prove it. So yeah, that would be an interesting question. Okay, so that's harder than I thought. Okay, so what's going to guide us is really something that comes from additive combinatorics, and I'm going to explain it now. So I'm going to give a small title. So approximate groups, and okay, this is very vague. Notions of boundedness. Okay, so when you study approximate subgroups, so let's fix one. When you study approximate subgroup here, there's a way of seeing approximate subgroup that comes back quite often in the literature or in different ways. But very abstractly, you could do something like that. You could define a distance on the group generated by lambda that is just going to be the word metric with respect to lambda. Okay, so let's define simply like that. That takes lambda mu and sends it to, well, I said it's the word metric, so simply to that. Okay, that's a very kind of rough and naive approach to looking at this approximate subgroup, but it kind of informs you on where we want to go. So, what are the few properties of this distance? So it's a well-defined distance. It's quite crude, but it's well-defined. But you can notice something that's quite interesting. So the ball of centered at the identity and of radius 1 is simply equal to lambda. You can go a bit further. The ball of centered at the identity of radius 2 is equal to lambda 2. And by the definition of approximate subgroups, which is just here, I know that I can put it in some lambda times f for m of f some finite. I can keep going like that. Okay. And what I know is that this is equal to lambda to the n. And this is just contained in lambda times fn minus 1. Okay, so it does not really tell us anything, but it shows us some sort of behavior here, that you have some pre-compactness or something, because this f to the n minus 1 is a finite subset, and what you're saying is that any ball of any radius is essentially contained in finitely many balls of radius 1. Yeah, so that's a nice behavior. It's not exactly nice enough to be used as such immediately in proofs, but that's where the various notions of models can come into play. So, okay, this is a vague notion, but essentially a model, because there are different notions of models, is a way to make this observation. So this observation that there's some sort of pre-compactness precise. Okay, so what could it mean to make this precise? It could mean various number of things. It could mean, okay, you're going to find maybe a finer, like another topology on your group, on the group generated by lambda, such that in this new topology, the BD lambda are actually pre-compact in the usual sense of the topology. This could mean anything like that. So trying to find a better model for lambda with this topology, maybe with a slightly richer topology that will tell you more about all of this. So it's very vague, but I'm just going to give a few examples of this very thing here. So what's really nice is that we have lots of examples of this kind of mindset. A first example of that, I'm not going to talk too much about it, is the ball sets. I think it's the right autograph. In the ball sets, you have some sort of approximate subgroup. It's finite, but what you're looking at is you say, okay, it's going to be, I believe, convex, correspond to some convex bounded set in some Rn or something like that, or torus or something like that. Okay, so that's a way to make this notion of these are bounded somewhere or compact somewhere more specific. So this is very nice, but it concerns finite approximate subgroups, so it's not really our topic today. Okay. A notion of that appears in Gromov's proof of the polynomial growth theorem of PGT. Interesting. This can be traced back to some work of Weil's on putting topologies on measured groups. This is really interesting because, well, this is a very early example of Weil's topology and measured groups. And let's say cousin of this, and a more recent one is the work of Reshkovsky and his stabilizer lemma. Okay, so Reshkovsky tells you that if you have just an approximate subgroup, it might be very large, it might be infinite, very, very infinite. As long as you have some notion of measures on at least zero measure sets around your lambda, then you will be able to define a very nice notion of model sets. And this is so precise that you can use it to prove the structure theorem of all finite approximate subgroups and so on. So this is a very powerful notion. Anyway, I could go on for quite a while, but I think I should try to speak about something else, or I should at least try to use these ideas a bit more. Okay, so why is it interesting to us? This word model is kind of used everywhere, but it turns out that it's related to the model sets we have here in a very, very direct manner. Okay. Should go climbing more often. Okay, and that's perfect because this is exactly what I'm going to talk about. The model sets. So how are the model sets linked to this notion of model? Well, I don't know if you've seen, but like I've added these assumptions that I've never used, that the projection of gamma is injective to G and dense to H. This essentially means that I can define the following map. Tau that goes from, let's say the group generated by M to H. And tau is just defined as follows. It is the projection to H and the projection to G. Okay. Since the projection of gamma to the projection of gamma to G is injective on gamma, given any element of the group generated by M, I can just go back and choose one element in gamma. That is the right element. Then I can just project it using P of H. Okay. And what you get is a very interesting thing. That's then M is simply equal to T minus 1 of the value 0. Okay. So this is quite reminiscent maybe of the definition of Bohr sets for those who study them, or of the work of Rushovsky. It's actually all in the same family of objects. And what it tells you is that, okay, maybe this distance was a bit crude, but at least if I go to this space H, I'm going to have a really nice notion of distance, which is going to be maybe a left invariant distance on the locally compact group H. And this is going to give me everything, well, very, very strong properties. Okay. So
does Meyer's proof use Bohr sets in some sense?
He doesn't use it, but his model sets appear for the same reason that Bohr sets appear in Freeman's work and everything. It all comes from the same kind of observations. Okay, so I'll call that the star map. Okay, this was already studied that way by Meyer. And I'm going to look at something. So what's happening here that's very interesting is I have this map 2 that sends my set M, which is discrete in the space G, to something that is compact in the space H. Okay, so I have G that I'm going to call a direct space, and H that I'm going to call the internal space. And what Tau tells me is that there's some kind of duality. Okay, I have the discrete sets here in my direct space, and their dual are just going to be the relatively compact space in H. And this is very reminiscent of, for instance, Pontryagin duality, or just Fourier analysis, essentially, the Fourier transform. And this is a very, very powerful idea. So what's going to happen is that to prove this theorem, we are going to first use what happens in the internal space to reformulate everything in terms of bounded cohomology. Bounded cohomology will appear naturally. And then use what happens in the direct space to show that this bounded cohomology is somehow tractable. It's not just a bounded cohomology of a weird object. Okay, so let's maybe tell you how bounded cohomology appear. And I don't think I'll be able to tell you any more than that, but that's already Nice. Okay. So to make this what I just said, so bounded cohomology appear kind of naturally there, I have to start working a bit. But what's nice is that all the intermediate steps, the intermediate results that we need are essentially also consequences of seeing approximate subgroups through that length of the boundedness or the models or something else. Okay, so let's call this subsection consequences of existence of models. Okay. So here, remember we have this situation here, and I'm just going to denote P the natural projection, just to put a name to put a name on it. Okay, and then kind of after these models or looking for these models or using the theorem that were developed, for instance, by Wachowski around this idea, you can prove a series of very interesting results. The first one being that you have some sort of, so your lambda is going to somehow decompose behave nicely with the decomposition that you have here, the natural decomposition that you have here. So what does that mean? You know that lambda squared, or let's put lambda 4 just to be a bit nicer. No, so this is a subset of Rn. I see Rn as just this normal subgroup that I'm going to denote lambda rad because it's in the radical of my group. This and also the projection of lambda to SLN R, which I'm going to denote lambda S. These two objects that are quite natural to consider once you have something like that are approximate lattices too. So R approximate lattices is well Rn and SLN R respectively. So this is, well, there are a few ways to prove that. But essentially, the first way was to just extend the null theorem of Mostow about intersection of lattices with radicals of the groups. Okay, you can actually go slightly further than that, and so the proof of that gives you something additional that lambda 4 is our Rn, so what I call lambda rad is in fact a model set. Okay, so that's really nice. So this is given by the proof. Actually, this is needed in the proof. And what you use there is some sort of like some weaker version of the stabilizer lemma of Wachowski. So as I said, all these ideas come to give this proof. Okay. And probably really nice result here is that I of lambda, so that I call lambda S, is also a model set. Okay, so you might have to modify slightly your lambda, but essentially it is a model set. So to prove that in that specific situation, you don't need much. It's relatively easy. What you look at is the action of lambda S on lambda rad, and you get some sort of arithmeticity from that. But in general, if you have a lattice in a semi-simple group, it's just it's a beautiful result of Wachowski.
Suppose you've taken a semi-direct product, but just took SLNR and an approximate lattice sub, whatever you're calling it, in SLNR n greater than or equal to 3?
It's you don't even need n greater or equal to 3. It's always a model set.
And if n is greater than 3, you show a model set. You have a result there. For some reason, you took the semi-direct product as your example. Why didn't you start off with SLNR n greater than 3?
Yeah, I could have started with SLNR. It's just because the story I'm interested in. So essentially,
I'm just trying to know what you know there, right?
This deal essentially, this result deals with anything that happens in an amenable group. So the amenable word is dealt with, and this deals with anything that lives in a semi-simple group. So if you have an approximate lattice,
It's a model set,
in a semi-simple group, it's a model set, and it's arithmetic.
and it's arithmetic.
Yeah, as long as it's not the value abstractions are
Okay.
So that's why it took.
So where do you use, and you use Margulis somewhere there?
You use Margulis to show that from model set you get arithmetic.
And which theorem of Margulis do you use there?
It's just arithmeticity.
But which characterization with commensurated?
Yeah, the easiest is commensurated. Okay, so here we have what we have managed to do is essentially we have our lambda in this group. And what we have managed to do is sort of decompose it into two smaller approximate lattices that we understand. So through the projection, we obtain lambda S, which is in SLNR, which is a model set. Okay. And through intersection, what we've obtained is lambda rad, which is in R to the n, which is also a model set. Okay. So you want to understand whether your lambda is a model set, and what you can do is decompose it and look at two smaller approximate lattices, and you know that these two are model sets as well. Okay, so the only thing you need to do is to find a way to come back up. And that's where the cohomology is going to appear quite naturally. To do that, what I'm going to do is, I know this is a model set, and I had this distinction between the direct space and the internal space. So if it's a model set, it comes with this product structure, with this product of two locally compact groups, and I'm going to denote V, the internal space. Of lambda. Okay. Okay, so I have this decomposition. Now I need to find a way to go back. Well, the way to do that is essentially quite understood. When you have an extension of two subgroups or an extension of two things, you take a section of your projection and you use it to define some cohomology, some cocycles. Okay, so that's what we're going to do. So we're going to study extensions of approximate subgroups, but we're going to just stay with that. Okay. So what I can do if lambda is any element of my projection of my lambda S, by definition, there is some element that I'm going to write S of lambda in the original approximate subgroup, approximate lattice, such that is equal to lambda. So what I'm taking here is just a section of my projection. Now, as it is well known, if you write this map with two parameters, which is the dot. Where lambda 1 and lambda 2 are lambda S. This is a two cocycle, sort of two cocycle because it's defined as something that's not a group, but essentially it's going to satisfy the same the same functional equality, which is just I have lambda one is a 2 cocycle. Okay, so 2 cocycle, but it's very abstractly defined. It's not clear that it's tractable. You don't really know what you can do with it. And that's where some magic appears. And what you can do is that now if I just take the projection of alpha to this SLNR, I just know that this is always equal to the identity just by the definition of it. Okay, so this implies that alpha lambda 1, lambda 2 belongs to the normal subgroup of Rn, but in fact, I know that this belongs to lambda, this belongs to lambda, this belongs to lambda, so I can intersect it with lambda 3 or lambda 4 even, and obtain something nice. So I have this 2 cocycle thing that also satisfies the fact that it always belongs to that set. And if you say in Rn, it's not clear what's going to what you can do with that set. It's just a discrete subset. It has not much interest. But if you look at it through the lens of the internal space, if you look at it using the model, what you know is that this tells you that this is bounded. Okay, so using the internal space, what you get is you get a way to send alpha to some alpha bar, which is going to write it very briefly like that. A bounded 2 cocycle from the S to V. Okay, so that's so I'm going to then say a few words on how we can understand that object, but essentially that's how all these ideas coming from the, let's say, more traditional, more classical study of approximate subgroups, and in particular finite approximate subgroups, kind of guides us to a very interesting object that is just going to be this bounded degree 2 bounded cohomology of lambda x. Okay. The only issue is bounded cohomology, as we know, is often quite hard to compute, and this is not a group. So it seems like you have 2 difficult ways, two things to overcome. But in this case, what you can do is, and that's something I won't have time to talk about, is you can also define the right notion of induction. Just like for lattices, you can do LP induction for this, and what you obtain is you get from these objects something in the degree 2 bounded cohomology of your group SLNR, which is already much nicer. But the coefficients become slightly complicated to understand because the coefficient stop being finite dimensional, and that's where you have to do a bit more additive combinatorics that I won't be able to present to you today. But all that to say that there is still a lot of work to do after that. But it's additive combinatorics that guides you all the way. Well, that's what I find very interesting. And so maybe to conclude, just to say something a bit more precise than the theorem, since I have 5 minutes. So let's say the crux of this theorem is proving the following thing: that if I have one of the 2 hypotheses there, so in the assumptions above, what I know is that there is an element G in Rn such that if I look at G minus 1, this approximate lattice will have a very interesting property, which is, as you know already, as I've told you, G lambda to the 4G minus 1 intersected with Rn is an approximate lattice. Okay, so that's not a surprise. But something that's much more interesting is that now you have that G lambda 4 minus 1 intersected with SLN R, where I see the usual copy of SLNR in this thing, which is, with SLNR is an approximate lattice as well. So in SLN. Again, so what does that tell you? It tells you that under these two assumptions, essentially lambda is also a semi-direct product of approximate lattices. And you have one of these lattices that is in a semi-simple group, and we understand them thanks to Reshevsky, and the other one is in an amenable group, and we understand them too. And so that's very nice. But since I have one more minute, what's very nice is that you can go further. And now you know that you can parameterize everything by this this thing here, the H2 of lambda S in V. Okay, and in fact, so what happens is that when this condition fails, so when the projection is a rank 1 lattice, essentially, this is going to be absolutely massive. This is infinite dimensional, I think uncountable dimensional even. So it's just completely mad. But each and every one of these classes is going to give you another approximate lattice in that group. And all of these new approximate lattices are going to have the problem that they are not Meyer and they're not arithmetically defined. And these are the only contour examples you can find, and they're all parameterized by this very nice object. Okay, so that's it.
Questions? Do you use anything specific about the module Rn? Do you do this for any just for SLN?
Yeah, you can do that for any linear algebraic group of a characteristic zero field. I guess positive characteristic introduces like further difficulties, but should be.
I was asking, I guess, something much more narrow.
Oh.
I was just thinking of replacing Rn by a very more interesting representation.
Oh yeah, any representation would be fine.
Okay.
So it's essentially, yeah, that's replacing Rn by an interesting representation is the only interesting case. You can always fairly easily reduce to that case, even if you start with a more complicated algebraic group. So
this cohomology in the higher rank case, it's known to be what, finite dimensional? I mean, you said it wasn't a group unit. You induce up to the underlying semi-simple group, you get a representation.
It's
And what?
If I'm not wrong, the map you obtain is just an isomorphism, so you get the same.
What do you use? I mean, you're not proving vanishing here of cohomology, right?
Well, yeah, no, you cannot really, because if you're.
I mean, it's finite dimensional. What is it?
It's so it's going to vanish fairly often. So as soon as your semi-simple group is not Hermitian, this is going to vanish. Otherwise, essentially what you say is that you have.
But I'm just trying to understand. Your theorem is going to use the vanishing thing.
Yeah.
What is that vanishing?
No, that vanishing. So the vanishing I really use is the vanishing. So you have a comparison map between the bounded and the just general cohomology of this. And what it uses is the vanishing of this like the vanishing of the kernel of this comparison map.
And who's that due to? I mean,
it's
bounded homologies.
It's just is, yeah, it's elaboration on what the Berger and Mono did.
Okay, so you're using that work.
Yeah. Well,
Okay,
it's
and that's an ingredient. And then you
it's an ingredient. So in this particular case, you have to modify a bit everything, but force, yeah, but essentially it's an ingredient. So there's a lot, there's a lot hidden in this vanishing theorem.
Okay.
Most of the work is hidden there, actually.
Yeah, and I'm just, I guess, I was wondering what you were using, and now you've said it, Monod Berger.
Yeah, Mono Berger, and you have lots of integrability issues that you have to solve. You have lots of things like that. But the main ideas are follow Mono and Berger Mono.
The questions? Well, let's thank the speaker again.